is an ordered pair G containing a set G in an operation which we'll call O times, consisting of a set G and an operation O times from G cross G to G, satisfying the following properties. Closure under O times. So for every X and Y in the set, X O times Y is in the set. Associativity. For every X, Y, and Z in the set, X O times Y O times Z is equal to X O times Y O times Z. A neutral element. There's a number G in the set, so that for every X, X O times E equals X equals E O times X. And an inverse element. For every X in the set, there exists a Y in the set, so that X O times Y equals E, which is equal to Y O times X. That inverse element is often denoted by X to the power of -1. We note that X inverse, or X to the -1, doesn't mean 1 over X in this sense. In fact, the function O times, or the operation O times that I keep referring to, can be any number of operations that we already know. Here's another definition. If this group has the additional property that for every X and Y in G, X O times Y equals Y O times X, then we call our group abelian. Let's take a look at some examples. The set of integers with the operation of addition is a group. Obviously, the first two properties hold. The neutral element is 0. And for every number A, negative A is the additive inverse. The natural numbers, however, so the counting numbers beginning at 0, with the operation of addition is not a group, since the inverses are largely missing. For example, there is no inverse in the set of natural numbers for 5. The set of integers with the operation of multiplication is not a group, since again, we're missing many inverse elements. The identity element in this, with this operation would be 1. And so, for example, 5 doesn't have an inverse because we can't multiply anything by 5 to get 1, at least nothing that's in the set of integers. The set of real numbers with the operation of multiplication is not a group as well. Our identity is 1, because 1 times any number is itself, but 0 has no inverse. There's nothing that we can multiply 0 by to get 1. Now, if we look at the set of real numbers without 0 and the operation of multiplication, this is in fact a group. In fact, it's an abelian group. The set of vectors, n-dimensional vectors of real numbers with addition, and in fact, n-dimensional vectors of integers are both groups with the operation of component-wise addition. So that O times that we were talking about before can be a variety of different normal operations. The set of regular or invertible matrices A of dimension n by n is a group with respect to the operation of matrix multiplication. In fact, we call it the general linear group and denote it by GL of n and r. Because we know that matrix multiplication tends not to be commutative, the general linear group is not abelian. To prove this, we note that for any n by n matrices A and B, we know that their product AB is also a matrix of dimension n by n. We note that for any ABC of dimensions n by n, A times B times C is equal to A times B times C. The identity matrix is our unit. And in fact, because these matrices are regular or invertible, A inverse must exist for any n by n matrix A. Therefore, the set and operation satisfy all the requirements of being a group. When we discussed groups, we looked at sets G and an inner operation on G, that is a mapping from G cross G to G that only operates on elements in G. We will now consider sets that, in addition to an inner operation, which we'll call plus, also contain an outer operation, which we'll call times. That's the multiplication of a vector x in G by a scalar lambda in R. We can think of the inner operation as a form of addition and the outer operation as a form of scaling. So a real valued vector space V is an ordered triple, V plus dot, consisting of a set V and two operations, plus and dot, where plus takes two things in V and outputs something in V, and dot takes a real number and something in V and outputs something in V, where the ordered pair V plus is an abelian group. 2 follows the distributive property. So for all real numbers lambda, vectors x and y, we have lambda times x plus y equals lambda x plus lambda y. And for every lambda and psi in R and x and v, we have lambda plus psi times x equals lambda x plus psi x. We have outer associativity for every lambda and psi in R and x in V. We have lambda times psi times x equals lambda psi times x, and an outer neutral element. So for every x in V, we have 1 times x equals x. These elements that we're talking about, x and v, are going to be vectors. And the inner operation, the plus, is regular vector addition. And the outer operation, the dot, is called scalar multiplication. To make things easier, in what follows, we'll denote a vector space, the triple v plus and dot, simply by a v whenever we're using our standard vector addition and scalar multiplication. Here are a couple of examples. If our vector space V equals Rn, so n-dimensional vectors with real entries, and we take normal component-wise addition and normal scalar multiplication, then Rn is vector space. If we take our V to be Rm by n, so the set of matrices with real entries of dimensions m by n, and we take matrix addition component-wise and scalar multiplication element-wise, then we have another vector space of m by n matrices. Finally, if V is a set of complex numbers with the normal definition of addition of complex numbers and multiplication of complex numbers, we again get a vector space. The third one obviously is a little different than the first two. Intuitively, vector subspaces are sets contained in the original vector space with the property that when we perform vector space operations on elements within this subspace, we will never leave it. In this sense, they're closed. Vector subspaces are a key idea in machine learning. For example, we use vector subspaces for dimensionality reduction. So as a definition, we'll let V be a vector space and let U be a subset of V with U non-empty. Then U is called a vector subspace of V if U is itself a vector space with the same operations, but restricted to U cross U and R cross U, rather than V cross V and R cross V. We write U as a subset of V to denote U as a subspace of V. Now, if U is a vector subspace of V, then U naturally inherits properties from V, which is very convenient. And this all comes from the fact that if X is in U, that means that X also has to be in V. So for example, if V is a vector space, every element in U is also in V, which means that every element in U has to follow the abelian properties, since we know that V is abelian. Same thing with distributive properties and associative properties. And the neutral element that will be in U also has to be the same neutral element that's in V. To determine whether U is a subspace of V, we need to show a couple of things. First of all, that U is non-empty. Particularly, we need to show that the neutral element is in U. And then we have to show closure. With respect to the outer operation, we need to show that lambda x is still in U. And with respect to the inner operation, we need to show that x plus y is still in U. So let's have a look at some examples. For every vector space V, the trivial subspaces, V itself, and the empty set, or the set containing the empty set, are subspaces. The set of solutions to AX equals B, with B non-zero, is not a subspace of Rn. However, if B equals 0, then the set of solutions to AX equals 0 is a subspace of Rn. In our next video, we'll explore the idea of linear independence and how that can be used in our study of linear algebra.